All right, welcome back, everyone. It's my great pleasure to introduce Lorenzo Foscolo from Sapienza Università di Roma, who will speak to us today about special Hermitian metrics on non-compact Calabi-Yau threefolds. So please, Lorenzo.
All right. So thanks very much for the invitation to talk in this series and to put it together and organizing it. And thanks for being here. Right. So what I'm going to present today is some joint work with Mario Garcia Fernandez. What I'm going to say is theorems we've proved, but sort of not yet appeared, and we're in the process of writing and understanding sort of what else maybe we want to add to this first results. Um, so I should also, encourage definitely questions and uh, comments from the audience as I'm sort of kind of new to this area. I'm sure I'll be missing various sort of um, references, and I welcome any comment that will help me understand things better and fit them better in what's known. So first of all, I'll introduce this 2B system, which or say what I'll call the 2B system. So this is 2B from 2B string theory, um, but is a sort of definite, well-defined system for a sort of. I'm going to be working with a real six-dimensional manifold endowed with what we call the SU3 structure. So here, little omega is a non-degenerate two form, and capital omega is a complex volume form, and they need to satisfy certain algebraic compatibility conditions. So pointwise conditions like little omega wedge capital omega is zero, and then normalizations of volume forms. And remind you sort of kind of it's convenient to think to start with just this pair of differential forms, but sort of the complex volume form automatically determines a almost complex structure J, and the sort of then this condition is saying that little omega is type 1 1 with respect to J. So I also have a metric G that's sort of induced by the SU3 structure. And then this 2B system is the following one. So we have our six manifold with an SU3 structure and then a positive function. And then we ask that these conditions, and I guess these equations appear in the physics literature, work of Thomas Yellow, Grania and others, and also in the sort of paper by Tseng and Yao. And maybe this particular equation, as I wrote them in the physics, to be the same as how they're written in the physics literature, I'm setting to zero lots of various fluxes. So let me comment. So what are these equations saying? So condition here for up to conformal factor e to the minus closed. So this implies that the almost complex structure is actually integrable, and then these sort of rescaled complex volume is actually holomorphic. Actually, this M is a complex threefold with trivial and holomorphically trivialized canonical line bundle. And then the Hermitian metric omega satisfies these two conditions. So these conditions, I guess better than me in this audience. So this is saying that omega is conformally balanced, and this condition is known as the pluriclosed condition. Okay, and then sort of, again, you know better than me how these equations sort of the kind of geometric in the context of geometry. One reason being interested of these sorts of equations, of variations of these equations, that they're related to questions about existence of canonical metrics on non-Keller Calabi-Yau threefolds. Okay, so let me make some immediate observation of this. So if omega is actually closed, so we have actually a Keller metric, then phi is constant. So really we're sort of our solution is actually a Keller Calabi-Yau, so a Keller-Ricci flat metric with a trivial, with a holomorphic, normalized holomorphic volume form, omega 0, and phi is constant. So, I mean, if you want a non-Keller solution, then one possible way to guarantee that, and is the main sort of situation we'll have in the examples that I'll describe. We, for example, ask that DC omega, which is a closed three form, is actually represents a non-zero cohomology class in the RAM cohomology. And then the sort of most important observation about this system is that this system definitely cannot have any compact solution. This follows easily, for example, by this consequence of the equation. So phi satisfies this equation, which implies that on a compact manifold, then phi must be constant, and then the solution is actually Calabi-Yau, Keller-Ricci flat. So if we want to find a non-trivial solution, then we need to either work on a compact manifold or allows singular solutions, or both things at the same time, which is what we're going to do. Okay, so these are the equations that we want to solve, and let's look at what non-examples are there. And so I learned this. So it turns out that there's various actually, I mean, there's a sort of a handful of non-examples, sort of known in the physics literature, for sure. And I mean, I'm not sure how, but again, here it's just might be my kind of sort of lack of preparation, but I mean, lack of knowledge of this field, but I'm not sure if they're widely known in the mathematical context. So the first source of examples is some explicit solutions of this system that arise from sort of dimensional reduction, essentially, and via sort of some sort of kind of conformal rescaling method that I mean, it's definitely present in old paper of Callahan, Strominger, and others in the physics literature, but it's also what's behind some of the early examples of these sort of conformally balanced metrics on non-Keller manifolds by Fu and Yau. So in this example, for example, the simplest thing that we can do, we take just our complex threefold, is just C times C2, and then I fix a harmonic positive function on C2, or maybe some open sets of C2. E to the phi is going to be the square root of this, and my Hermitian form is just the product of the standard flat metric on C and this conformal rescaling of the flat metric on C2. And well, a positive harmonic function on an open set of C2, there's not very many choices. And so well, we need to allow sort of if the function is defined on the whole of C2, then it must be constant. And sort of otherwise, the simplest thing that one can do is allow isolated singularities at a bunch of points. And if we assume that these points are finite, then basically the choice of harmonic functions are just given by this. So we have some positive function, some non-negative function, well, I mean, some constant C some other constant alpha prime, a bunch of distinct points on C2, and then I can allow some multiplicities if I want to consider point coalescing. And then sort of what happens with this matrix. So first of all, if this parameter alpha prime is zero, then well, the metric is just flat. So it's Kähler-Calabi-Yau. Uh, the simplest non-Kähler solution, I guess, is taking C to be zero and just one singularity. And then this metric is nothing but the isometric product of C with what I think is called the Boothby metric on C2 minus the origin, but it's just, the C2 minus the origin is R plus times S3, and this is just a cylinder metric. So that's the simplest thing, but sort of you can then some sort of contributions at different points, and then this constant C is sort of determining the asymptotic behavior at infinity. So if C is positive, then the metric at infinity is asymptotically Euclidean. And if sort of C is zero, then you would have this cylindrical behavior at infinity. Right, so basically, so this is going to be a metric that has sort of n plus one ends. One end is the one at infinity, and then there's these n cylindrical ends coming from these points that you've removed. And sort of kind of if you think of DDC omega as a current on the whole of C3, then this is satisfying DDC omega equals some sum of delta currents of integration along certain holomorphic curves, which are just C times the points that I've deleted in C2. Okay, these are some simple explicit solutions. And then it turns out that there's two other sort of solutions that are explicit, but a bit more complicated. And they, again, as far as I know, please correct me if I'm wrong, but they do appear in some physics paper, sort of in work of Chamseddin Volkov and Maldacena Nunez from sort of late 90s, early 2000. And so I'm going to talk this solution as the CVMN solutions, which is also what they were called in a number of papers in the physics literature around that time. So let me start with the first such example that's sort of I guess, easier to explain. So first of all, I recall we have a complex manifold, which is just a complex threefold. And so here, the complex threefold that we take is the so-called resolved conifold. So this is just so I'm taking P1, I take rank 2 complex vector bundle over P1, which is O minus 1 plus O minus 1. And then I'm going to remove the zero section. Okay, so this is a C2 minus the origin holomorphic fibration over P1. And for example, one way of recovering this CVMN solution is trying to fiber our sort of Boothby metric over P1. Right? So I have a C2 minus the origin fibration over P1. I could try to cook up a solution that is sort of a fibration where the fibers are Boothby metric on C2 minus the origin, the cylinder metric on C2 minus the origin, and then I have Fubini's 2D on the sort of horizontal directions. And it turns out that this doesn't quite work. You need to, but there's a sort of correction to this, which is just sort of, if you conform or rescale it, the Fubini's 2D metric on P1, via a function that's basically a constant plus there's a logarithmic term. So, and
And is
turns
the
out,
T here is like the cylindrical direction in the Booth
yeah,
T?
correct. Yes, yes.
And is this complete?
Well, I'm going to say this
Oh, okay.
now.
Yeah. Okay.
So basically, this logarithmic term, the reason that you need to do this correction is basically coming from some sort, I don't know, maybe a physicist would like to say it's the back reaction of the sort of curvature of the Chern connection of O minus 1 over P1. So you sort of start with a kind of, I don't know, adiabatic limit ansatz, fibering Booth B over P1 using the Chern connection of O minus 1. And then, well, the fact that the Chern connection is not flat is sort of telling you that you need to do a modification, and that's forcing this term. So what is, to understand what this metric looks like, you can just look at the Riemannian metric induced by this, and you sort of pass from, I mean, essentially f of t equal s is a geodesic distance on this for this metric, and then the matrix looks like something like this. Where, so here, what I'm saying is that sort of I look like GS2 is just a metric on, I mean, Fubini study metric on P1. Here I write GS3 for a sort of metric on S3, which in this simple example is just a round metric on S3. And but really here, I mean, the manifold is not S2 times S3, is really an S3 fibration over P1, uh, where I'm using the Chern connection of O minus 1 to write this metric here. Okay, so what's happening to this is basically as uh, S goes to infinity, I have a complete uh, end where basically I have I don't know, the sort of S equal constant, sort of large balls in this metric look like Riemannian submersions, where the fibers are S3s or with some fixed metric, and the base is P1 with a sort of is an S2 of diameter square root of S. And as S goes to zero instead, you have some singular behavior. So this would be so it's a solution that is not complete. It has a singularity as we go inside, but is complete as I go towards infinity. Right? And that's one thing. And then um, also in the physics literature, there's another explicit solution that I'll also call the CVMN solution. This now lives on what's known as the deformed conifold. So this is as a complex manifold. This is just the affine hypersurface inside C4 cut out by this equation, x squared plus y squared plus z squared plus w squared equal 1. As a smooth manifold, this is dysbiomorphic to T star S3. And then what you can do, you can write down an explicit solution of this 2B system, so an explicit conformally balanced pluriclosed metric that is completely smooth on T star S3, but at infinity looks like it has this complete CVMN behavior. So this Riemannian submersion where the fibers are three spheres of some fixed radius, and then the base, well, is I mean, sort of large spheres are Riemannian submersion with fibers that are S3s with a fixed metric, and the base is a sort of S2 of diameter square root of the distance.
I'm sorry,
Yes.
where does it appear? This one? Is it in these papers that you mentioned?
Yeah.
It's in like the Maldacena and Nunez?
Yeah.
Okay. And I guess maybe I just want to make sure I understand. So, you just say sort of pluriclosed and conformally balanced, but in the end, these do have vanishing Bismuth-Ricci form, is it right?
Yeah,
As well.
yeah,
I
isn't
guess
that,
is
I
that's
mean,
equivalent
well,
in
because
the
it's
context of SU
SU3.
structures, I guess. Because I
So
guess it's maybe not
these
equivalent.
are these are the equations that I'm solving. So I guess the Ricci vanishing bismuth because here omega is a sort of normalized. So I'm starting with an SU3 structure, and
Right.
then I guess the same function that
Yeah.
appears here in the conformally balanced equation is the same
Yeah.
that makes capital omega closed. Yes, indeed.
Okay. Yeah. Thank you.
Yeah. All right. So these are known solutions. Okay, and then the question is, so these are non-solutions. So again, on the resolved conifold, there is something that is kind of forward complete, but it has some singularity that, however, I mean, is a bit sort of exotic in the sense that, I mean, I wasn't aware of any sort of kind of other interesting metric that has this type of behavior. But I mean, sort of once you introduce this CVMN complete end and singular end, then we have these two examples on the resolved conifold, the singular solution that is, however, forward complete, and on the deformed conifold, a perfectly smooth complete solution. And now the question is, can you produce more solutions? And then, well, if you look at these particular solutions that are sort of explicit, then here the reason that they're explicit is that actually they enjoy a very large symmetry group. So there's a nice kind of SO4 or up to final cover SU2 times SU2 symmetry, which is sort of the SO3 symmetry, I guess, is obvious here. So, and these metrics, sort of these symmetries preserve the complex structure, and these metrics are kind of invariant under this SU2 times SU2 action. So, a first strategy is look for kind of the more general SU2 times SU2 invariant solutions of this 2B system. So that's I'll return to this, but there's another sort of route that leads to a different, but kind of in the end related strategy, which is sort of kind of starting from asymptotically conical Calabi-Yau threefolds. So I told you that my 2B system contains, as a very special case, solutions that are just Keller-Ricci flat, stroke Keller-Calabi-Yau. In that case, the dilaton e to the phi is just a constant, and then my SU3 structure is just Calabi-Yau. We need to look at non-compact solutions, so very large and completely understood class of complete non-compact Calabi-Yau threefold is the one of asymptotically conical Calabi-Yau threefolds. And there's been a lot of activity around this, involving many authors. And finally, very recently, complete classification in terms of complex geometric data of these asymptotically conical Calabi-Yau manifolds due to Conlon and Hein.
Sorry,
So here,
what's the meaning of the dilaton here?
it's just a
What's
constant,
oh, it's just you. Okay. Okay. Yeah. Fine.
right?
Yeah.
But it will
Yeah, yeah, sure.
serve. I mean, it has no. I mean, it's no purpose here. But I could. I mean, it will appear later. I'll deform around this to
Sure,
non-Carrier
sure.
solution, and then this will be some sort of expectation value for the dilaton at infinity, you would say. So, okay, so here asymptotically conical, what does it mean? So here's a picture that I stole from some other talk. So here B should be M. So I have a manifold with a metric that sort of, well, first of all, we need to introduce what's a cone. Riemannian cone is just, so I have a, so in this dimension, I have a five-dimensional closed connected manifold, Riemannian. And then the sort of Riemannian cone over sigma is just R plus times sigma with this metric dr square plus r square g sigma, where r is a coordinate on this r plus factor. So I mean, this is a kind of cartoon picture of what this metric looks like. And then if we want this cone to be Calabi-Yau, then the five manifold sigma must be Sasaki-Einstein. So, and then my asymptotically conical manifold will mean that I have some complete metric that's sort of outside of a compact set, looks like the cone, so it has some fall-off behavior that sort of is natural to impose to be sort of polynomial at, I mean, some fall-off behavior at some polynomial rate. Okay, so there's lots of okay. I had forgot that I had this. So my asymptotically conical Calabi-Yau structure outside of a compact set looks like the conical Calabi-Yau structure plus terms that decay together with all derivatives at some polynomial decay rate. Okay, so as I said, there's tons of these asymptotically conical Calabi-Yau manifolds. And in particular, the deformed and the resolved conifolds are well known to admit sort of asymptotically conical Calabi-Yau metrics that are due to Candelas de la Ossa and Stansel in the early 90s. And these metrics are explicit again because they enjoy SU2 times SU2 invariant, SU2 times SU2 symmetry. So, so given that you have lots of kind of Keller solution of the 2B system, then one possible question or strategy to try to produce new non-Keller solution would be to try to deform an asymptotically conical Calabi-Yau manifold to some asymptotically conical non-Keller solution with sort of small torsion. So measure, for example, by asking that the cohomology class of DC omega is small. Okay, so and the results that I want to present is basically sort of where we can go following strategy number 1 and strategy number 2, and I'll start with strategy number 1. So I'll sort of describe existence of solutions of this 2B system that are SU2 times SU2 invariant. And I mean, actually, one can show that sort of the choice of this particular group acting in the way that we do is actually the only one that leads to interesting solutions. But anyway, so okay, so I have a six manifold now. What's the setup? So let me describe what's the setup. So I have a six manifold M that is acted by SU2 times SU2 with homogeneity 1. So this means that there's an open dense set M star on my manifold that is just sort of foliated by hypersurfaces, which are homogeneous spaces for my group SU2 times SU2. So there's this open set that's diffeomorphic to R times a homogeneous space for SU2 times SU2. And I'm going to make the assumption that the homogeneous space is just SU2 times SU2 divided by the diagonally embedded U1. Right, and this is sort of exactly the type of homogeneity one um, um, kind of structure that you get when you look at the form and the result conifold. So we have two possible complex structures, the complex structure of the form conifold, the complex structure of the result conifold that we introduced before. And we make some, we fix, so we want to look for SU2 times SU2 invariant solutions of this 2B system on, at least on this dense open set. There's basically one free parameter. If I'm assuming symmetry, then there's only one free parameter. So I want to reduce my PDE system to a system of ordinary differential equations. So there's some obvious background choices, sort of topological choices that you need to make. One is the cohomology class of the sort of DC omega. And another one is sort of what I'm calling the Keller class, in the sense that once I'm fixed, I mean, because of the symmetry, once I fix the cohomology class, essentially there's a preferred representative of DC omega. Then I sort of fix, the complex structure is fixed, so I can fix one form such that DC omega prime is this specific representative. And then this unique SU2 times SU2 invariant representative, and then sort of that involves fixing omega prime, involves perhaps sort of, I mean, there's the freedom of to adding a closed 1 or closed 2 form there, so there's some choice to make. And once you make this choice, then the only free variable is a sort of function that depends on this one variable R, and satisfying the 2B system reduces to I mean, you can write it as a single second order ODE for this function U. So S is a parameter on this R, and here V and U0 are two functions of R that depends on the R explicit and depends on the choice that I make. So which choice of complex structure I've chosen, which cohomology class, and which sort of background close to form I've chosen.
What is eta?
Eta is the contact one form on SU2 square.
Okay, that's what I.
So I mean, this is basically my Sasaki-Einstein manifold. There's actually a unique SU2 times SU2 invariant one form eta that turns out to be the contact one form associated with the homogeneous Sasaki-Einstein structure. Right. Thanks. Right, so here I haven't written, but I don't know. So for example, if I work on the resolved conifold, V is e to the 3s, and U0 is something like a constant times log s plus another constant, and sort of these two constants are determined by these two cohomology topological choices that I make at the beginning. Right, so so this is the system. What are known solutions of this system? Well, if if d omega is cohomologically 0, then it turns out to actually be 0. So I have Calabi-Yau metrics, and so there's the kind of explicit asymptotically conical Calabi-Yau matrix of Candelas de la Osa and Stenzel that can be written, I mean, that will give explicit solutions U to this equation. And there's also the CVMN explicit solution that I discussed before that gives also some explicit solution U star of this ODE. Okay, and this is the theorem that we've proved. I put 2026 star since well, the hope that well, I mean it should appear at some point this year on arXiv soon. I mean this year meaning soon. So what is it that we find? So up to natural rescaling and symmetries, discrete symmetries. There are two one-parameter families of interesting solutions of this system. So if I work on the deformed conifold, then there is one-parameter family of perfectly smooth, complete, non-Kähler solutions of this 2B system that are asymptotically conical. On the sort of resolved conifold, actually, one can prove that there will never be smooth solutions, but we can find a one-parameter family of solutions that have sort of at infinity that are complete, asymptotically conical. But as you go towards the sort of zero section inside, then they become singular and have a singularity modeled on the CVMN solution. Now, in sort of for both one parameter family, they're asymptotically conical. In particular, the dilaton phi converges to a constant, phi infinity. And this constant phi infinity can be taken to be the parameter in the family. And then basically, when this constant goes to minus infinity, I get as a limit of the solution the explicit CVMN solutions that were already known. And when I go at the other extreme, after rescaling, doing some appropriate rescaling, I converge to the asymptotically conical to the other non-solutions
And so
that are
can I ask the
Kähler-Calabi-Yau.
slice is S2 cross S3, right? A-
Yes.
And so you kind of only have like what you have sort of one choice of the Kähler class and one choice of the torsion class, I guess, right?
Yeah.
And but then somehow up to scaling, that just works out to one parameter. This is another way to think about what the parameter is, I guess. Is your
No. So, well, so, okay. So, for example, if you work on the deformed conifold, for example, there's no Kähler parameter because, and you want something smooth, then, I mean, the omega sort of, I mean, there's no Kähler parameter, but there's a parameter coming from the choice of complex structure. I mean, there's the
yeah.
period of the holomorphic volume form.
Okay.
And then there's another parameter which is the expectation value of the dilaton at infinity. And then there's a third parameter which is the torsion, the cohomology class of the DC omega.
Oh,
Uh,
oh, okay. Oh, okay.
but there are symmetries, and the symmetries are scaling
Yeah.
and I mean, shifting the dilaton by a constant.
Uh-huh. Yeah.
That's how you're left with one parameter. And then for the resolved conifold, instead, I mean, there's no parameters in the choice of complex volume form, but there's instead a Kähler parameter
Okay.
plus the choice of torsion class plus the expectation value for the dilaton. But then again, 2 degrees of freedom by scaling and conformally, I mean, shifting
Okay.
the dilaton by a constant.
Okay. And do they form a smooth family with the Calabi-Yau guy?
What does it mean, smooth family?
Well, is there a just like as metrics? I mean, are they deformations of
Well, so I
do they
mean
converge back to the
the
Calabi-Yau?
place where it makes sense is like the deformed conifold, since these are all smooth metric on the same smooth manifold, then yes,
Yeah,
there's a infinity convergence on compact subset of T stars 3, the other end of the
yeah, yeah. Okay.
right. Okay, so let me make some comment about this. So it turns out that in the physics literature, so Maldacena and Martelli in 2010 have a paper where they speculate about the existence of this one parameter family, sort of somehow speculate about the existence of a one parameter family of solutions that deform the CVMN solution. I mean, they have nothing rigorous, but there's some convincing argument based on numerical approximations and some matched asymptotics. And then I should also mention earlier work by Alonso and Salvatore on trying to classify homogeneity 1 SU3 structures, and then basically using these results, homogeneity 1 balanced SU3 structure, and then using your result, you basically um, reduce to, I mean, can deduce the fact that SU2 times SU2 is the only, well, I mean, with sort of the kind of homogeneity one setup that we consider is the only interesting one. Right. So, okay, I have a slide about trying to prove this theorem. Um, so try to kind of a very kind of hand wavy kind of explanation of what goes behind proving this theorem is not so trivial in the sense that um, I mean we prove existence. I mean, this is the theorem is an abstract existence theorem. We don't have explicit formulas for these solutions. So the argument goes something like the argument for existence goes something like this. So so first of all, you construct kind of short time essentially solutions. So in the case of the form conifold, you construct one parameter family of solutions that are defined that are smooth and defined in a neighborhood of the zero section in T star T star S3. And in the case of the resolved conifold, you construct a one parameter family of solutions that have this model singular behavior provided by this CVMN solution. So, and then you want to study which of these members of this one parameter family exists for all time and sort of what's the asymptotic behavior. And that's where it gets a bit involved. And so the Stuman step, so I'm a bit involved. I mean, it requires some analysis. And the Stuman step, one is about sort of proving that solutions exist for all time if the sort of parameters lie in a certain range. And so this is based on some comparison argument for this ODE system. And then to control the behavior at infinity, you need to control the growth at infinity of this solution. And this is done by sort of essentially understanding the evolution of this ratio of where you compare the function, the sort of unknown solution u with the explicit solution coming from the CVMN
Oh,
solution.
yeah. This U star is like the is a Kähler. This sort of corresponds to a Kähler metric,
No,
or
no, U star is
oh,
the
oh,
CVMN,
yeah. Oh, okay.
the explicit non-Kähler
I
solution.
see.
Yeah. All right, so that's where strategy one, so looking for homogeneity one solution, led us to these two interesting sort of one parameter family of non-Kähler solutions uh, that kind of one can say interpolate between the Kähler ones and these I mean, really, if you can, I mean, if the choice of cohomology class you label it of the torsion you label it alpha prime, then the CVMN solution should really be sort of some strongly coupled limit in the sense that if you use this rescaling freedom that you have, then the limit where the CVMN solution appears is the same, I mean, is equivalent to a limit where this alpha prime goes to plus infinity.
I see. So wait, sorry, just so I'm totally clear, like this CVMN one is not actually in your family. It's like a limit of things in your family.
It's a limit, but for T star, I mean, it's a limit in the sense that, and it's not in the family in the sense that is at infinity. I mean, for T star S3, so it's a one parameter family of smooth solutions. So they kind of generically they're all asymptotically conical, so they have some fixed common behavior at infinity. And then this CVMN solution, I mean, near on compact sets, you have perfectly smooth convergence, but at infinity, there's a jump of asymptotic
Right.
behavior.
Right. Okay. Thank you. Yeah.
Right. Okay, so what about the other strategy? So the other strategy number two, I recall was about sort of deforming some asymptotically conical Calabi-Yau threefold. So for example, what you can do is the following. So you start with an asymptotically conical Calabi-Yau threefold that's asymptotic to some Calabi-Yau cone C with some decay rate mu. And then I fix my dilator is a con. And then I'm also fixing a cohomology class of degree 3 with a topological constraint. So the basically my uh, this cohomology class must contain a representative H0 such that if I apply J to it, then I get uh, exact um, exact three form. Okay, and then the theorem is that basically there is a one parameter family of non-Kähler solutions of this 2B system that were sort of parameterized by a parameter alpha prime that should be very small. All the solutions are sort of asymptotically conical. So the SU3 structure is asymptotic to the conical Calabi-Yau structure on the cone, and the dilaton is asymptotic to this constant that I've chosen at the beginning. These solutions are non-Kähler if alpha prime is non-zero because the cohomology class of the torsion of H is multiple of my chosen non-trivial cohomology class. And as these are deformations of the Calabi-Yau solutions in the sense that when alpha prime converges to zero, then these solutions converge back to the Calabi-Yau. Sorry, these two shouldn't be there. Converge back to the asymptotically conical Calabi-Yau structure. Okay, so let me say very quickly, I guess this type of result is not, it's not so surprising that I start with a Kähler solution and I perturb. So what goes behind this? I mean, of course, there's going to be some application of the implicit function theorem. So the main point is understanding understanding the linearization, and understanding the linearization is essentially about understanding what might call the weighted Epley cohomology of an asymptotically conical Calabi-Yau manifold. So you look at 1-1 forms that are DDC closed and have a certain decay rate, and then you want to find representative for kind of equivalence classes given by uh, so the usual definition of Epley, but where you're imposing some control on decay rates, since we work in this non-compact world. And then basically what happens if your form sigma decays faster -2, then things work as in the compact case. So this, I mean, we're on a Keller manifold and things work in the compact case. So this Epley weighted epic homology is just the same as H2. So closed and co-closed form. But if you cross this threshold -2, then there are actually non-closed classes. I mean, classes in this that are represented by non-closed forms. And actually, this weighted epic homology is kind of basically if nu is larger than -2, but sufficiently close to -2, then is a how to say, is an extension of second cohomology of my manifold by piece that can also be understood via a cohomological term, and it's the image of the third cohomology of my asymptotically conical manifold into the third cohomology of the boundary. So sigma is the boundary of this asymptotically conical manifold. And so that's what's behind the theorem. And I guess what's interesting is that you can get so first observation is that this theorem applies to infinitely many examples. So for example, you can take this affine variety. So uh, um, so you have P and Q, these are two integers that must satisfy this condition and cannot be coprime. So this first condition arises from essentially K stability. So the existence of a Calabi-Yau cone metric on the sort of what's the candidate cone, tangent cone at infinity, and the sort of necessity and I mean the sort of the existence of a I mean, the existence and I don't know the characterization of existence of this Calabi-Yau cone metric in terms of this condition is due to Collins-Székely. And then sort of you definitely the existence of asymptotically conical Calabi-Yau metric on this affine smoothing, then follows by work of Collin and Hein. And then basically this condition is necessary to guarantee that this sort of non-closed piece of the Hapley cohomology to be non-zero. So basically this follows from Milner study of the topology of these affine varieties. And so in this way you can get infinitely many examples, and so you got infinitely many complete non-Keller solutions, and then I guess of this 2B system. And I guess an interesting observation, I mean, of course, this 2B system cannot have compact solutions. And I mean, there's an observation about the holonomy of the Bismuth connection of these solutions that are produced by this theorem B. Because the holonomy of this Bismuth connection must be the whole of SU3. That's basically because of this asymptotically conical condition. So the Bismuth connection is asymptotic to the Levi-Civita connection of the cone, which does have full holonomy SU3. And I think I'm over time, so I'll stop. Thanks.
Yeah, thank you. Are there more questions? I already asked, I think most of mine.
Sure.
Um, uh, yeah, let's see. Well, okay. I mean, I guess if there are no other questions, yeah, let's just thank Lorenzo again.
Thank
And
you.
yeah.